Unit 13. For the last couple of weeks of the course, we're going to look at some atomic and nuclear physics, starting with the outer part of the atom. If you've taken a chemistry course, some of this will sound familiar. Physics and chemistry kind of overlap, well, in several places, this being one of them. Chemists think that it's chemistry, but of course we physicists know that it's actually physics. To explain the structure of the atom, this isn't quite the order that things were discovered in historically, but one fairly logical way of looking at it is if you start with the concept of wave-particle duality, because that explains a lot of what goes on inside of atoms. Not long ago, we were looking at interference of waves. And I mentioned how that shortly after the year 1800, experiments, the first one being done by Thomas Young and other experiments later done by others, demonstrated that light is a wave. Before that, there had been two schools of thought, where some people, such as Christian Huygens, thought that light was waves, and other people like Isaac Newton thought that light was a bunch of particles, sort of an atomic view of light. Just like matter is made of atoms, light is also made of some sort of little things. Well, particles would not diffract, you wouldn't get interference effects. And so that seemed to settle the question for 100 years or so. But around 100 years later, in the closing years of the 19th century and the opening years of the 20th century, a number of experiments showed light behaving like a bunch of particles. So neither picture is perfect, okay? If you want to think of particles like baseballs or balls colliding on a pool table, that sort of thing, yeah, sometimes light sort of behaves that way. But other times it's more like ripples on a pond or something like that. So maybe a better picture of light, instead of the classical picture of, the ripples moving across a pond like this, these would be the wave fronts, and the rays here just show the direction that those waves are moving. I mean, light does have a wavelength and a frequency and those sorts of wave-like particles. So maybe instead of a continuous wave like that, if you think of it as being a whole swarm of little microscopic wavelets, more like this picture over here, even that is not a perfect picture. But, well, it gets a little closer anyhow than this picture over here. So think of light as a lot of little flashes rather than a continuous wave like you see on a pond. Each tiny little flash of light behaves in some ways like a particle. These particles that aren't really exactly particles, but anyhow, they're called photons. The energy of each photon depends on its frequency. So for example, a photon of violet light would have a higher energy than a photon of red light, because violet has a higher frequency. The proportionality constant between the two is a fundamental constant called Planck's constant, which, if you're measuring in SI units, is this very small number here. So this first problem for you to work on, that's just a matter of, I'm asking you to drop numbers into, well, actually, it'd be a two-step thing, wouldn't it? Because it gives the wavelength, not the frequency. So a couple of steps. You have to calculate the frequency from the wavelength, and then put the frequency into this to get the energy given here. So you know the drill by now. Pause the recording. And now presumably you have unpaused it and may need to see me run through it. My cords are caught on the computer here. Problem number 1, section 13. Yes, that looks like that does show on the camera. So I did the algebra first and dropped the numbers in at the end. I said E equals HF, and then I substituted, I should write that down here, from a few weeks ago, F equals, was that section 9, I think, when I started covering waves. The frequency of any wave is equal to its speed divided by its wavelength. Well, fill this expression in for the frequency. The speed of light in a vacuum is usually represented by the letter C. Letter V is usually used for other speeds. And then fill in the numbers. Planck's constant. I think on your formula sheet, I took it one more decimal place. So if you really want to be a perfectionist, 6.626 times 10 to the negative 34, but yeah, it's close enough for the kind of thing we're doing now. Speed of light in the vacuum. In meters per second. There again, if you want to really be precise about it, 2.998 times 10 to the 8th. (500 nanometers). Nano means 10 to the minus 9th. Your calculator should accept it like that, or although standard form would be 5 times 10 to the negative 7. Well, whichever way you put that in the calculator, it should come out 3.98 10 to the negative 19 joules. Well, this was worked out in the early years of the 21st century or 20th century. E equals HF goes back to some work that Max Planck did in 1900. The idea of photons goes back to Einstein's explanation of the photoelectric effect in 1905. You get into the 1920s, and along comes this guy, and I'm down here now at this point. I should probably raise this thing up pretty soon, but I think every teacher I ever had pronounced this poor man's name differently, and I'm not going to do him justice. I never took French, so yeah. I think it's de Broglie or something like that. I've heard people say de Broglie, which, well, anyhow, the guy's name is not the point. Point is that he says, you know, what's so special about photons? If they have this dual nature, where in some situations you have to think of them as particles, and in other situations you have to think of them as waves. Maybe that's true in general. Maybe it's not just photons. Maybe anything has a wavelength. So he generalized the idea that we were just talking about at the top of the page here, and said, you know, electrons, all sorts of different things, could have a wavelength equal to Planck's constant divided by their momentum. And this sat around for actually not that many years. It's like, man, this is kind of an interesting theoretical speculation. And I think it was, don't quote me on the date, but maybe 1927, when a couple of guys who were conducting an experiment for an entirely different purpose accidentally noticed that they were diffracting electrons off of a crystal, the electrons behaving exactly like X-rays would. You see, if you want to do diffraction experiments with X-rays, the wavelength of X-rays is 1,000 times shorter than the wavelength of light, which means if you wanted to make a diffraction grating for X-rays, you'd have to have the lines 1,000 times closer than the lines on a grating made for visible light. Well, you're talking about putting scratches on a piece of glass that are separated by a single atomic diameter. And yeah, that's not going to happen. But fortunately, you don't have to make a grating for X-rays. Naturally occurring crystals, because of the way that you have the orderly arrangement, planes of atoms in a crystal, the way they will reflect X-rays off those planes of atoms is fairly, a few details are different, but it's fairly similar to how light is scattered by the scratches on a grating. And so you can do interference experiments with X-rays by shooting them at a crystal. I think in Davidson and Germer's experiment, it was a piece of nickel that they had accidentally crystallized. That anyhow, the electrons appeared to be exhibiting interference, an interference pattern. And follow-up experiments, like it says here, neutrons were being diffracted. I think it was 1930 when somebody was able to diffract whole neutral helium atoms off of a crystal and get an interference pattern. So this wacky sounding idea, within a matter of a few years, was experimentally confirmed. What I always say is nature by definition is perfectly natural. So if you see something in an experiment that seems bizarre, must have been your expectations that were bizarre. Because like I said, nature, perfectly natural. Anyway, you have this dual nature for basically everything. So boosting the page up a little higher still, the next exercise for you to work on is to calculate the wavelength of a 75 kilogram person running 5 meters per second. And I'll move the camera while you've got it paused. Planck's constant divided by the momentum. De Broglie's idea applies, I probably said it differently than I did the last time. You know what you need to do if you really care about this is I think there's some website where it'll tell you how to pronounce things, and you put the guy's name in there, and what is this in French, and some little voice will do much better than I am. Anyway, Planck's constant divided by this person's momentum. You see, the thing is, Planck's constant is a really small number. And that's a lot of zeros after the decimal point. So, mass times velocity is momentum. So this person has a really small wavelength. For a comparison, I mean, never mind the 1.7 in front. It's the order of magnitude. How many zeros after the decimal? Um, the diameter of an atom is around 10 to the minus 10 of a meter. The diameter of an atomic nucleus is around 10 to the minus 15 of a meter. 10 to the minus 36, that's seriously small. And the reason I'm making such a fuss about that is that this is the reason that you don't notice wave behavior for ordinary everyday objects. Like, a person runs through a doorway. Shouldn't you get some sort of single slit interference if a person is also a wave? Well, in principle, yes, but in practice, the amount that they would get displaced, the features of the interference pattern, they are separated by amounts that depend on the wavelength. It was A sine theta equals m lambda for where the destructive interference occurs. And so anything measurable is related to the wavelength. If you calculate the angle that you might get shoved to the side one way or the other because of single slit interference when you run through a doorway, the angle is completely unmeasurable with any imaginable technology. The way you draw an angle that size is you put the vertex of the angle at the center of the Milky Way galaxy in the constellation Sagittarius, about, about 26 or 28,000 light years away. From that point, you draw lines to opposite sides of an atomic nucleus here on Earth. That's your angle, okay? That's how much, that's the angle in the equation for single slit interference for something with a wavelength that small. Completely imperceptible. If it was 1,000,000 times bigger, it would be completely imperceptible. So for all practical purposes, wave behavior does not exist for people and baseballs and airplanes and anything you encounter in everyday life, which is why classical pre-20th century physics works so well. And that's why we still teach it to people, even though technically it's kind of sort of wrong. But it works, and it's much simpler than the more sophisticated modern models that you have to deal with if you bring this kind of thing into it. So anyhow, somehow what I just ranted and raved about for about 5 minutes became 2 sentences here. That's what happens when you have time to think about what you're going to say instead of just saying it. But because the wavelength is extremely small, the amount you diffract running through a doorway is too small to measure. So you don't notice the wave nature of everyday life. Oh yes, and then the little demonstration I like to do. So wave behavior, particle behavior, they're as different as night and day, different as black and white. How can something be both a wave and a particle? Well, it occurred to me one day that I could demonstrate the same sort of duality if I just took a little blob of correction fluid, that paint you use when you make a mistake on a piece of paper. And I put it on a little piece of plastic right there. And what I always do is I walk up to a student, and it shows up a little better back here, I guess. And I say, what color is that? And when the camera isn't doing something weird, the student looks at it and says, oh, well, that's white. I say, okay. And then a second, I'm going to flip a switch. And I walk over to a different student, and I take my little piece of plastic here, and I hold it up like that so it's backlit. And I say to the student, well, what color is that? And well, it's not exactly black, it's more of a gray kind of thing, but well, you know, if you're not being too picky, you could call that black. And so question becomes, if black and white are as different as night and day, how can something be both black and white? Well, it depends on how you look at it. If it's front lit, it's white. If it's backlit, it's black. And in the same way, photons or electrons or whole helium nuclei or whatever it is you're talking about, they look like waves, they look like particles, depending on how you look at it. In this kind of experiment, they look like waves. In that kind of experiment, they look like particles, just like my little blob of correction fluid there. When you look at it front lit, it looks white. When you look at it backlit, it looks black-ish. So, you know, oh, these scientists, they can't even figure out whether light is really a wave or a particle. Well, is light really a wave or a particle? It's just a bad question. There is no answer to it. It's just like, is that blob of correction fluid really white or is it really black? It's just a bad question. Or another variation on how to think of it that you hear sometimes when people are trying to explain this kind of thing is, imagine there was a couple of blind people. And they're going along one day and they happen to encounter an elephant. And they're trying to get an elephant figured out. Apparently, this is a very patient elephant because it just stands there and lets them explore. But I guess when you're that big, you can afford to be patient. You know, it's always the little dogs that are the yappy mean ones. The big ones, they just kind of look at you and go, whatever. But anyhow, there's this elephant. And the one blind guy has got hold of its trunk and he's kind of groping up and down it. And he said, well, you know, an elephant's like a snake. And then the other person's got hold of one of the elephant's legs and says, no, an elephant's like a tree. And well, snake, tree, neither one is really a very good description of an elephant. But you know, if that's all you understand, if that's all that's in your experience, well, snakes and trees, what you're going to have to do is sometimes think of the elephant as a tree and sometimes think of the elephant as a snake and go jumping back and forth between those two pictures, depending on the situation. So that's anyhow, that's some sort of an idea of the idea of wave particle duality. So with that as background information, let's see if I'm going to make it to the bottom of the page. I need that just a little higher. And a little more focused. You know, whatever happened to cameras where you could just grab the ring around the lens and turn it and focus things? But I guess that's just too primitive. Anyway, the Bohr model of hydrogen. We talk about hydrogen a lot when you're first introducing people to this kind of thing, because hydrogen's the simplest atom, okay? You've got a proton, you've got an electron orbiting around it, end of story. That's the whole system, just a nice little two-body system, as opposed to maybe a uranium atom, where you've got a nucleus and 92 electrons whizzing around it, all interacting with each other. I mean, I don't even want to think about how many different ways there are pairing those up anyway, hydrogen is the simplest. And actually, if you get deeper into it, then than we will in this course. Hydrogen is the only atom where everything can be solved in closed form, even in helium, unless it's ionized helium, which is almost the same thing as hydrogen. But a neutral helium atom, even that you have to start resorting to approximation methods, because a three-body system is quite a bit more complicated than a two-body system. So as you probably are aware, if you had taken chemistry, if you haven't taken chemistry, well, I guess I'll tell you now. The electrons in atoms have energy levels, okay? An electron can orbit the nucleus only at certain special distances. It's not like putting a satellite in orbit around the Earth. I mean, in some ways, a hydrogen atom is like the Earth-Moon system. Okay, you've got the moon orbiting around the Earth, like the electron orbiting around the nucleus. But one of the important differences is you can park a satellite in an orbit around the Earth, in any orbit you want. No restrictions. Planetary mechanics is very easygoing in that respect. In an atom, on the other hand, you can put an electron in orbit this far from the nucleus, or this far, or this far. In between, not allowed. So Niels Bohr came up with that idea in, I'm pretty sure it was 1913. It was another decade before the reason why was explained by de Broglie's hypothesis. So the Bohr model of hydrogen, as later explained by all this lambda equals h over p kind of thing. Think back a few weeks to the lab we did on standing waves, the one where there was the long spring and you shook the one end with your hand and you made the different standing wave patterns. And you calculated what the resonant frequencies ought to be, and then you set up the standing waves and actually counted out the cycles per second, and they were supposed to match. The condition that had to be met in that lab is that if a wave leaves your hand, goes down, reflects off the wall, comes back to your hand again, to leave your hand and get back to your hand has got to be a whole number of wavelengths, okay? Down and back was one wavelength. That was the fundamental mode of vibration. In other words, the length of the spring would be half a wavelength in that case, but leave your hand to get back to your hand would be a whole wavelength, down and back. Down and back equals 2 wavelengths was the next allowed mode of vibration, and the third one was when down and back was 3 wavelengths, and so on. Well, instead of having waves travel along a line like you did in that lab, what if they traveled around a circle? Like, you know, if you had a circular trough with some water in it and you were poking the water with your finger to make waves that would go around and around this trough. Well, it's the same condition in that the allowed wavelengths, if you're going to set up standing waves, is that from leaving your hand and going around and getting back to your hand has to be a whole number of wavelengths. So circumference of the orbit has to equal 1 wavelength, or 2 wavelengths, or 3 wavelengths, for the same reasons that we saw in that standing wave lab several weeks ago. So the circumference, we're talking about, you know, an electron is a wave. Thinking of an electron as being like the moon orbiting around the Earth, well, you know, that's like when the blind guy has the elephant's nose. But sometimes you have to think of the elephant as a tree. And thinking of an electron as a wave rather than as a moon-like particle, as that wave goes around the nucleus, the circumference of its orbit, circumference of a circle is 2 pi r, has to equal a whole number of wavelengths. N is a whole number, like it says over here. In the innermost orbit, n equals 1. In the next allowed orbit, n equals 2. The one beyond that, n equals 3. If you've taken chemistry, this thing is called the principal quantum number. And if you haven't, don't worry about that. So the electron can only exist at certain distances from the nucleus. If you apply some Newtonian mechanics and Coulomb's law, the energy of the nucleus the energy of the electron, I mean, depends on its distance from the nucleus. Just like, I just happen to have a random metal weight sitting here on the desk for reasons that have nothing to do with this, but the farther I get it from the Earth, the more energy it has. Potential energy equals mgh, for those of you who took the first course, 121. Well, just as moving this thing higher in a gravitational field makes its energy more, moving an electron higher in the nucleus's electric field increases its energy. And so saying that the electron can only exist at certain distances from the nucleus amounts to saying that there are only certain energies the electron can have. Lower the page back down. So skipping over all the mathematical details and going for the thing with the box around it. The energy, now I suppose one thing I should mention is that the Bohr model turns out to be an oversimplification in some ways. One of those ways is that it assumes circular orbits, which actually turns out to be not true. Another thing is the Bohr model assumes that the electron just follows a circular path, that it's basically a one-dimensional wave moving along, a bent line. That also turns out not to be true. But in spite of its shortcomings, the Bohr model does calculate the correct energy levels for hydrogen, and also it can be used in approximation methods with heavier atoms. And so while it's oversimplified, it can be a useful picture to have in your head because, simple is nice when you can get away with it. The energy here is measured in a unit called an electron volt. 1 electron volt is this tiny little fraction of a joule. Electron volts are more convenient for atomic work for a couple of reasons, one of which is it's a better size. You aren't always dealing with something that's got a decimal point and then a bazillion zeros. It's also defined in a way that's convenient for people who are using particle accelerators, where you've got charged particles that you're accelerating through a certain number of volts. An electron volt means the energy that an electron gains if it passes through a potential difference of 1 volt. People doing atomic and nuclear and elementary particle physics almost always measure energies in electron volts rather than joules. So I guess you better get used to it. This is actually, E here stands for the total energy, kinetic plus potential. The minus sign is, well, of course, the kinetic energy is always positive. You can't have a negative kinetic energy, but the potential energy is negative if an electron is in a bound state, okay? So, and the potential energy is bigger than the kinetic energy. So when you add them up together, you get a negative number. A positive energy means a free electron, okay? An energy of 0 is the minimum. Well, let's put it this way. The thinking goes like this. If you had the nucleus and you had an electron extremely far away from it, so that it was basically where the electric field from the nucleus, where the electric field from the nucleus was 0, that's thought of as a situation where there's no energy. okay? If the electron then falls toward the nucleus so that its energy becomes lower than that, well, if it has an energy of 0 when it's at rest very far away, then when it gets closer, its energy would be less than 0. So the conventional way of looking at things anyhow is that an electron which is bound to a nucleus has a negative energy. A positive energy means an electron which is escaped from a nucleus, a free electron. And energy is 0 is the borderline between the two. That's what's up with the minus sign. Oh, terminology. Unless the gas is really hot, then most of the atoms are in what's called the ground state, which means the electron is in its lowest energy level, n equals 1, okay? If the atom has been given a jolt of energy so that the electron is in a higher energy level, then those are called excited states. An atom with more energy than the ground state is said to be excited. So I guess the idea is I'm going to do an example, and then after that, you're going to do an example. That got fuzzy on me, didn't it? I guess you can still read it. But it looks better. So if you need to read the example, there it is. And part A, what's the wavelength of the electron? I'm going to find that by using that condition on the bottom of the previous page, where it says the circumference of the orbit has to be a whole number of wavelengths. N, the quantum number, is how many wavelengths. So, well, I should just start writing it out. Okay. Part A. A little bit further that way. Okay. N equals 2 means the circumference of the electron's orbit is equal to 2 wavelengths. When n equals 1, the circumference is 1 wavelength. N equals 3, the circumference is 3 wavelengths, and so on. The circumference of a circle is 2 pi r. Well, 2's drop out, and so the wavelength is going to be just pi times the radius. And maybe I'll put it down here. A nanometer is a billionth of a meter, 10 to the minus 9. So now that's the wavelength of the electron, not to be confused with the wavelength of any light it might give off. Two different kinds of waves there. Part B, what is the electron's energy when it's in the n equals 2 state? So part B, the energy of the nth energy level. That's what the subscript is not terribly important, but that's what it means. the energy for this particular value of n minus 13.6 if you measure in electron volts over n squared. Just fill in the value of n given in the question, and we've got negative 3.40. C says how much energy is lost when the electron drops to the level below this, n equals 1. Well, what you have to do is repeat the same calculation using n equals 1 to find out how much energy the electron will have after it drops. And the difference is the amount lost. Okay, the electron had this much before, it had this much afterward. How much did it lose? You subtract the one from the other. So energy of level number 1 is minus 13.6 over 1 squared, which, divide by 1, not too tough. 13.6 electron volts. Well, that's not the answer yet. I'm getting ahead of myself. Put the box around the wrong thing here. Question is how much energy was lost? So I have to subtract these. I could go into some sort of an explanation about, well, you have to subtract them in this order because this is the reason why, but maybe the quick way to say it is just there is no such thing as a photon with a negative energy. Okay, the energy of a photon is a positive number, period. So don't get distracted by the minus signs, just subtract the things and get a positive number. And that's the short version of the story. So 13.6 minus 3.4 the electron lost 10.2 electron volts as it fell to a lower level. If you want to get nitpicky about minus signs, the energy change of the electron is negative because the electron lost energy. But if you phrase the question, how much energy does the photon have? Well, the energy lost by the electron equals the energy gained by the photon, so that would be a positive number. Well, it says how much energy is lost when it did. Anyhow, it's that many electron volts. So finally, the wavelength of the light given off. Well, that brings us back actually to, still over here in the corner, remember question number 1 that I did a while ago? The energy of a photon is related to its wavelength by E equals hc over lambda. So if I know the energy, and h and c are fundamental constants, I can look them up, then I can solve for the wavelength. There's just one little detail, which is the values available on your formula sheet for the speed of light and Planck's constant are in SI units, meters and kilograms and so forth. So electron volts is going to have to be converted to joules so that the units play nice together. So first step is to clean up the unit that the energy is measured in. And then it's E equals HC over lambda, solve for lambda. So you've got the conversion factor right up there at the top of the page, or maybe more importantly, if you're in the middle of a test, it's on the table of units on your formula sheet. The usual question is, you could just look up the conversion factor, but should you multiply by it or should you divide by it? As usual, you figure that out by canceling units. So 1.6 times 10 to the negative 19 joules equals 1 electron volt. EVs over EVs cancels out. And this comes out 1.63 times 10 to the negative 18 of a joule. If you set it up the other way around, so it was 1 over 1.6 times 10 to the negative 19, then you'd come out with square electron volts per joule, which does not sound like something you really want. Now that the units are fixed, since wavelength, again, going back to unit 9, the wavelength of any kind of a wave is equal to the speed divided by the frequency. From E equals HF, if E is equal to HF, F is equal to E over H, which, if you simplify it, is HC over E. Drop in the numbers and we'll have the answer. Planck's constant, speed of light in a vacuum, and the energy of the photon in joules. The answer is 1.22 negative 7 of a meter, which is down in the ultraviolet part of the spectrum. The way it works out for hydrogen is that when the electron drops all the way to the ground state, you get a photon in the ultraviolet part of the spectrum. The ones in the visible part of the spectrum are when an electron drops into n equals 2 from somewhere higher. And if an electron falls into the third or fourth or anything higher than that, from a level that's still higher, then you get photons that are in the infrared part of the spectrum. You don't actually have to remember that. I just kind of threw that in for a little background information. So I have, of course, a problem on here for you, which is similar to the one that I just ran through. Basically, the only difference is I started out with the electron in the third level instead of the second one. And then after that, it drops into n equals 2 instead of dropping all the way to n equals 1. So changed a couple of numbers. Aside from that, and I didn't break it down into 4 parts like I did in number 3, but it's the same question with the numbers changed. So pause it, try to do it yourself. And if you can't do it yourself, maybe do it yourself after you've watched me do it to see if you can do it then without peeking. So guess I'll write it out over here. Number 4. Once again, circumference of the orbit equals a whole number of wavelengths, that whole number being 3 this time. So as usual, you can put in the numbers first and then do the algebra, or you can do the algebra first. You know, I did the algebra first. Lambda equals 2 pi r divided by, well, yeah, I might as well do that now. N is equal to 3, because it says so in the question. There's a little formula for the radius, but we aren't going to get into that. It's just given in the question. So the wavelength 2 pi times 0.476 nanometers. So the answer will come out in nanometers. 997 of them. And again, this is the wavelength of the electron, not the wavelength of the light that electron will give off when it falls to a lower energy level. In the other one that I did a minute ago, the wavelength this is the wavelength of the light. It was like 100 times longer than the wavelength of the electron. So they're two distinct things. So then part B. The basic idea is you calculate the energy before the electron falls, you calculate the energy after the electron falls. The difference, the amount of energy that the electron lost, equals the energy that see, it always gives off just a single photon. The electron moves from the one energy level to the other almost instantaneously. I mean, there's a very short time interval allowed by the uncertainty principle, and we aren't going to get into that either. But to a good approximation, you can think of the electron as just disappearing from here and appearing in the other energy level pretty much all at once. And so it doesn't have the option of giving off a lot of little photons along the way. It has to just give off one sudden flash of light as it falls. So it's a single photon as the electron makes that transition. And the energy of that little flash of light is the difference between the two energy levels. So the energy of the third level, 13.6 over 3 squared, 1.51. And the energy of the second level is something I already did when I was doing the other example. Once again, that's 13.6 over 2 squared, which comes out 3.4. And so 3.4 minus 1.51 It's 1.89 electron volts, which is the energy of the photon that's given off. Well, then there's that thing about being consistent with the units on H and C. So convert that into joules the same way I did before. So 3.02 times 10 to the negative 19th joules is the energy of this photon. And last step, or you could think of it as a couple of steps, I suppose, but yeah, let's write it out as 2 steps. Might be easier for you that. I kind of combined things when I did it before, but if E is equal to HF, that implies that F equals E over H. So 4.57 times 10 to the 14 hertz is the frequency of this light. And kind of squeezing it in on the bottom, what was asked for was the wavelength. Times 10 to the 8 over that number I just calculated. Yes, I have not gone off the bottom of the screen. 6.59. -7. People quite often talk about wavelengths rather than frequencies because wavelength is what's measured by a spectrometer when you get into the experimental side of things. Well, speaking of the experimental side of things, as far as the history of the topic goes, that's what came first. Next thing down the handout here says spectra. It says look at lights from some source through a grating, or you could use a prism, but most spectrometers use gratings. Depending on what the light source is, you'll see one of 3 different types of spectra. And I have my handy spectrum chart over here. I took it down off the wall. So you might see a continuous spectrum, like you've got across the top here. This thing's been hanging on the wall for quite a while, by the way, and some of the colors are kind of faded and not quite true to life anymore. But the idea of a continuous spectrum is that it's like a slice out of a rainbow. Okay, you've got every wavelength present from what's supposed to be dark red on the one end to violet on the other end without any gaps or anything like that. You get a continuous spectrum from one thing from a hot solid, like the filament in an incandescent light bulb gives off a continuous spectrum, okay? A thin gas gives off some sort of a bright line spectrum. So maybe I should get you a little closer. The one on top is mercury vapor. Let's turn it so there isn't any glare on it. You've got a red line here We got another red line here. All the wavelengths in between are missing, okay? Got actually a little cluster of yellow lines over here, kind of a greenish one there, and so on. Some violet. It goes on into the ultraviolet. A thin gas, if you make it glow, gives off only certain special wavelengths. All the others are missing. And then the third possibility is an absorption spectrum. So what do we have here? Well, doesn't matter which element it is. The point is, it's kind of the opposite of a bright line spectrum. You have here a dark line spectrum. Instead of only certain special colors certain special wavelengths being present, only certain special wavelengths are absent. You have a continuous spectrum with dark lines going across it at certain frequency or certain wavelengths. I should maybe point out also that each different, trying to tilt it so we don't get glare off the overhead lights, each different chemical element has its own characteristic pattern of lines. Here's hydrogen down at the bottom. Being a relatively simple atom, it's got a pretty simple spectrum. You've got a red line there and kind of a blue-green line over here, a couple of violet lines over on the edge. Some of these other elements are a lot busier, but the point is each chemical element has its own characteristic pattern of lines, which serves as a fingerprint you can use to identify an unknown substance. I'm going to go set this thing down. This, for example, is how we know what stars are made out of. There was, when was that? Like in the 40s? Some philosopher guy, physicists just love to laugh at philosophers. Actually, we shouldn't, but he was philosophizing about things that obviously must remain forever beyond human knowledge because, you know, these are our limitations. And one of the things he mentioned was the composition of the stars. What are stars made out of? How could we ever know that? Yeah, it was only about 25 years later that Kirchhoff came along and laid down, with the same Kirchhoff we talked about in electricity, with the point rule and the loop rule. People didn't confine themselves to subspecialties back then the way they do today. It was only about 25 years after that that Kirchhoff laid down the rules of spectroscopy that you use to do exactly that, figure out what stars are made out of. The photosphere of a star gives off, that's its apparent surface. I mean, stars do not have a surface, but the photosphere is the layer that's dense enough to be opaque. So it looks like the surface of the sun, even though it's actually just another layer of gas. The photosphere gives off a continuous spectrum. But then as that light rises through the upper layers, certain wavelengths get absorbed, okay? See, I guess I never quite finished the story. A cool gas will absorb the same wavelengths that it would emit if it were glowing. So I shouldn't have phrased it that way because the atmosphere of the sun is not exactly cool, but well, hot gases can absorb light also. They just turn right around and emit it again right away, but perhaps off into a different direction. Anyhow, the so-called atmosphere of the sun imposes absorption lines on the solar spectrum. And so you do that fingerprint thing that you can identify which elements are doing the absorbing by which wavelengths have been absorbed. So where am I on the script here? A continuous spectrum is one where all wavelengths are present. An emission spectrum is one where only certain wavelengths are present. You get a pattern of bright colored lines on a dark background. This again would be after the light passes through a grating. An absorption spectrum is when you pass a continuous spectrum through a gas. It will absorb the same wavelengths it would emit if it was hot. I said that. So this was all originally observed in the 1800s. By the late 1800s, you get into like the 1890s, turn of the century, around into that time period. They had really good spectrometers by then. They learned how to make really good diffraction gratings and could measure wavelengths nice and precisely. Nobody could explain why line spectra existed at all, let alone explain the patterns in the wavelengths of the lines. By the early 1900s, by trial and error, formulas had been worked out, mathematical formulas for the wavelengths in the spectrum of hydrogen. It's like, the way these lines are arranged, these wavelengths look like there's some sort of a pattern in what the wavelengths are. And, after a great deal of calculating and trial and error, they had some nice little formulas for, this series of lines obeys this formula and that series of lines obeys that formula. Nobody could explain why line spectra existed at all, let alone explain the patterns, the formulas for the wavelengths of the lines. The atomic nucleus had been discovered a few years earlier, which actually was an additional problem, because according to classical physics, if you've got electrons orbiting around a nucleus, the orbits should be unstable. The electrons should give off what's called synchrotron radiation, lose energy in the process, spiral down into the nucleus in a fraction of a second. And since matter appears to be stable, that's an observation that seems to be inconsistent with theory. Anyhow, 1913, along comes Niels Bohr and says, what if atoms had energy levels? And these spectral lines are from electrons jumping around between those levels. Matter is stable because the electron can't go any lower than the lowest allowed energy level. And anyhow, basically what Bohr proposed was the calculations that you just did, okay? He went through this process, except instead of filling in specific numbers, n equals 3 and n equals 2, he just left it all in terms of n initial and n final, and was able to derive the relationships that had been seen in the spectrum of hydrogen. And that made everybody sit up and take notice, even though Bohr had kind of made some ad hoc assumptions, which is a fancy way of saying he pulled a rabbit out of a hat once or twice. But as I said earlier, 10 years later, the reason for these energy levels could be explained in terms of the wave-particle duality. So no one could explain line spectra until Niels Bohr suggested. Bohr, by the way, Einstein gets on all the t-shirts, but Bohr was no drooling idiot either. And he was fairly close to Einstein, actually, in his stature in developing quantum theory and, early 20th century physics in general. Anyway, Bohr suggested the electrons are restricted to energy levels, photons. I've already said all of that. So based on doing this sort of thing, he derived this, there it is, there. The equation in the box, that's the wavelength, that's every wavelength there is in the spectrum of hydrogen, or at least the wavelengths in and around the visible part of the spectrum. Exactly matches hydrogen's observed spectrum. So I've got a problem here for you to work on. I probably ought to put this thing up where you can read it in case you're trying to do this without a copy of the handout next to you. That needs to be a little higher. Could just document share this, but it's just easier to switch back and forth if I just do it this way. So, yeah, it's a little crooked higher on the left, but you can read that. It's a repeat of problem number 4. But instead of I made you go through it step by step yourself, so you would get a close-up look at how an atom works. Well, now that everybody hopefully understands that, why not just build the whole process you went through into this handy little formula? All you have to do is drop the 2 and the 3 in there. What I've labeled final and initial, by the way, assumes an emission spectrum. If it's actually an absorption spectrum, then the one I labeled F would be initial and the one I labeled I would be final. Okay, an electron emits light. If it falls to a lower level, an electron absorbs light if it jumps to a higher energy. So anyhow, you do that while I erase the board over here. And then I'll write it out. Good. Number 5. Quicker and easier. 1 divided by the wavelength equals this number. It's called the Rydberg constant, and I'm sure you didn't care. So this would be 1/4 minus 1/9, which you could do it as a fraction. I punched it up in decimal form, 0.13, and then a repeating 8. So that times this number gives you 1.52 10 to the 6th power. And then there's always somebody who forgets the last step. This is not the wavelength. This is 1 over lambda. So the wavelength would be the reciprocal of that. When I did it the other way, I got 6.59 instead of 6.56. Well, if I carried the numbers out another decimal place, there wouldn't have been any difference, but the way the numbers were rounded caused a little bit of a difference in the last decimal place. Time to once again turn the page. Looks like the next thing is to say a couple of words about stimulated emission. There's actually 2 different ways that an atom might give off light: spontaneous emission and stimulated emission. And spontaneous emission is because of the fact that the excited states are unstable. I guess I can go a little higher on that. It's kind of like a flower pot sitting right on the edge of a shelf someplace. You know, one day a truck happens to drive by the house and it falls off. So excited states are unstable. In most substances, you only have to wait a small fraction of a second. I mean, in many cases, a really small fraction of a second, and the electron falls back down again. It may not go to the ground, like if it's in n equals 5, it might drop right straight to the ground state in one jump, or then again, it might stop at some other energy levels along the way down. In that case, you'd get more than one photon given off. But that's spontaneous emission. Stimulated emission is if before the electron has a chance to just fall down on its own spontaneously, if you knock it down to a lower energy level instead, then you've stimulated the atom into emitting a photon instead of it just doing it spontaneously. You can't knock the electron down with just anything. If you shoot a neutron or something at it, that's not going to work. It's got to be a photon. And furthermore, it's got to be a photon identical to the one the atom is going to give off. So this example I did back over here with hydrogen a while ago, this particular transition gives off a photon whose frequency is 4.57 times 10 to the 14th hertz. If along comes a photon that's 4.58 times 10 to the 14th hertz, no, sorry, that's not going to work. To stimulate emission, both photons have to be the same. And then the two photons, the incident photon and the one the atom emitted, then move away from that atom in phase with each other. That's one of the characteristics of stimulated emission, is it gives off coherent radiation. The photons are lined up with each other, crest to crest and trough to trough. Stimulated emission is used in lasers. That's the main application. I can't exactly think of any other important applications of it, but lasers are important enough. You see them everywhere these days. Grocery store checkouts, and doctors using them in surgeries, and the list goes on and on. So laser is one of those words that's made up of the first letter of a bunch of other words. I guess it's called an acronym. Light amplification by stimulated emission of radiation. So the S and the E, if you spelled laser with a Z, I'm sorry, that just doesn't work at all. The S and the E in laser stand for stimulated emission. The most common lasers these days would be some sort of a solid state laser, actually, some sort of a little diode that gives off laser radiation. But, well, this is the kind of laser that we use here in the lab. It's a gas laser, a helium neon laser. And a greatly oversimplified picture of it is here. So you've got a gas in a glass tube. In the case of a helium neon laser, it's a mixture of helium and neon, mostly neon. It's like about 90% of the atoms in there roughly are neon atoms. And you pass an electric current through it to make it glow. This is the same way that the gas discharge tubes we use in the lab in here work. It's the same principle as a neon sign on the side of some sort of a business. If you shoot a lot of electrons through a gas, when the electrons collide with the gas molecules, they will give those molecules a little jolt of energy and kick them up into an excited state. Well, before long, the electrons return to the ground state, giving off light as they do so. That's actually not only what goes on in a neon sign, but in there's fluorescent lights all over the ceiling in here. They're full of mercury vapor that is made to glow by the method I just described. The difference is the inside of the glass is coated with a fluorescent material that makes the light whiter than it would be if you just simply had a tube full of mercury, a clear tube. Anyway, using the same sort of stimulation method that you see in a neon sign or a fluorescent light, passing an electric current through the gas excites the atoms in there. Now, one thing you need for a laser is a substance that has an excited state that will last a fairly long time, because you need to get a lot of the, well, in this case, it's just atoms, helium and neon don't really form molecules, they're inert. But atoms or molecules, whatever kind of substance you're talking about, you need to get a lot of them all excited at the same time. And it's a lot easier to do that if there's an excited state with an unusually long lifetime. So anyhow, floating around inside this tube are a whole bunch of excited neon atoms. And then one of them spontaneously gives off a photon, which starts traveling through the gas. Well, the gas it's traveling through is full of other excited neon atoms. And before very long, this photon runs into an atom and causes stimulated emission. And now you've got these two coherent photons moving along together. And before very long, they run into other excited atoms, which give off even more photons. And you see, it's the same transition in every atom, the same initial and final energy level. So they all have exactly the same frequency. And, they're identical photons. And the process kind of cascades. The ends of the tube are mirrors. So the light goes back and forth through the tube over and over again, causing more and more stimulated emission. The mirror on one end is partially silvered, by which I mean, the way you make a mirror is you take a piece of glass and you deposit some metal atoms on it. And for a regular mirror like you might have in your bathroom, they put the metal on there thick enough to reflect pretty much all the light that hits it. A little bit gets absorbed. But what if you were really stingy with the metal atoms so that it was like a really thin coating on the end here? If you were stingy enough that there was only a little bit of metal deposited on there, you could allow, well, pretty much whatever percentage you wanted, depending on how much metal you put in your mirror, to leak through instead of be reflected off. So some of the light gets reflected, actually quite a bit of the light gets reflected back, but some, a decent amount also leaks out, and that's where the beam emerges from the tube there, and that's the laser, okay? The beam that comes out is fairly directional. It's coherent because of the nature of stimulated emission. All the little wavelets are marching along in step with each other. And it's monochromatic. It's a single frequency because all of those photons were given off by the same transition in the same kind of atom. So stimulated versus spontaneous emission with applications. Well, as I mentioned earlier, the Bohr model of the atom is actually an oversimplification. And if you continue the story through the 1920s, they ironed out the wrinkles. There is, for example, in a lot of spectra, there's fine structure. What look at first glance like spectral lines, like I was showing you on the chart, yeah, if you got a really good spectrometer and look at them really closely, they're actually multiple lines. There's fine structure, lines that are really close to each other. So things like that remain to be explained. And when they finally did, it turns out there's more to it than just the main energy levels that I talked about with the Bohr atom. So a more detailed analysis shows the main energy levels contain sublevels. If you took chemistry, there's actually 4 quantum numbers, not just n. The complete description, N, L, ML, and MS. L and M describe or the orbital angular momentum of the angular momentum is something I've never talked about in this class, but so I probably shouldn't even mention that. In the ground state, n equals 1, there are two possible combinations of these numbers. N equals 2, there are 8 possible combinations of these 4 quantum numbers that includes n equals 2. In the third energy level, I didn't write it down here, but I believe the number is 18 possible combinations of quantum numbers that include n equals 3 and so on. And this isn't a chemistry class, and I'm not going to dwell on that. Take chemistry for details. But there's this thing called the Pauli exclusion principle, which says that no 2 electrons in an atom, and it's actually not just electrons, other particles, protons and neutrons, for example, also obey the exclusion principle. But at the moment, we're talking about electrons. No 2 electrons in an atom can have all 4 quantum numbers the same. At least one of the 4 numbers has to be different for any 2 electrons you look at. So, since there are only 2 combinations of quantum numbers that include n equals 1, that means if you have a multi-electron atom, there can only be 2 electrons in the n equals 1 energy level. There are only 8 combinations of the numbers that include n equals 2, so you can only have 8 electrons in that second energy level, and so on as you work your way up. So this often gets called the shell model of an atom, which is kind of an oversimplification. The waves, electrons are waves. The waves are actually 3-dimensional. They don't just confine themselves to some sort of a circular orbit. And the wave functions overlap with each other, and it's not as simple as a bunch of nested shells. But well, again, an oversimplified model simplifies things. It's convenient when you can get away with it. So for many purposes, you can think of 2 electrons in an innermost shell orbiting farther out. You've got 8 electrons in the second shell, and so on. And again, take chemistry for details. I spent about 5 or 10 minutes there talking about what a chemistry class spends like weeks and months on, depending on how far into it you get. But let's take one more step. And instead of, first I was talking about an atom with just 1 electron, and then multi-electron atoms. And let's go to an even more complicated system, which would be a collection of many atoms, also known as a solid. So a solid is many atoms forming a regular geometric pattern called a crystal lattice. For ordinary crystalline solids are like that anyhow. There are also amorphous solids where you don't have a crystalline lattice. And this would be something like glass, for example. Materials like this, actually at the microscopic level, if you go down to the atomic level, they actually resemble liquids more than they resemble a crystalline solid. They just don't really flow. But any true solid, any crystalline solid, you've got this geometric pattern called a crystal lattice. In the case of water, for example, it's a hexagonal pattern. That's why snowflakes have 6 sides. In the case of table salt, it's a cubic pattern. If you look closely at grains of salt, they look kind of like little cubes, and so on. Graphite, like the so-called lead of a pencil, it's actually carbon, not lead, and the atoms are arranged in a hexagonal pattern. If you rearrange the atoms into, I guess it's not exactly a tetrahedral pattern, but it's just called the diamond pattern, but it's more or less a tetrahedral pattern. It's you have a diamond instead of a pencil if you just switch to a different crystal lattice for how the atoms are arranged. So anyhow, that's the nature of a solid. When you put a lot of atoms in close proximity like this, the neighboring atoms kind of disturb each other's energy levels so that they spread out into bands. You know, you have a single atom, like I was talking about hydrogen, and it's like, yeah, there's this energy level, and when the electron is in it, it's got negative 3.4 electron volts, and that's the exact amount of energy that the electron can have. Yeah, in a solid, you've got a whole range that, you know, the electron can have any energy from about there to, you know, from there to there. You still have energies in between which are not allowed, just like in an atom, you know, in hydrogen. The ground state is minus 13.6 electron volts. The next level up was negative 3.4. All the energies in between are forbidden. You can't have an electron in a hydrogen atom whose energy is negative 8 or negative 9 or negative 5, or, you know, that's in between is not allowed. And you've still got in between energies that are not allowed in a solid. It's just that the energies that are allowed are kind of spread out into bands, corresponding to the energy levels you'd have in single atoms. Now, the example I have here is sodium, which is a metal. I just copied it out of a textbook. The textbook authors thought sodium would be a good idea, but other metals would be something similar. Sodium, each sodium atom has, I believe it's 11 electrons if it's a neutral atom. There would be 2 electrons in the ground, you know, the n equals 1 energy level. So if you have a little tiny piece of sodium metal that's got, let's say, 1 trillion atoms in it, that means there would be 2 trillion atoms with n equals 1. The that energy level kind of spreads out into a band in a piece of metal like that. So those 2 trillion electrons are filling up this innermost band. This as you go up the picture, energy increases. Horizontally, it doesn't really mean anything, but as you go up vertically, these are supposed to be higher and higher energy bands. So next, you've got the electrons with n equals 2. Well, as I mentioned earlier, in multi-electron atoms, you've got sublevels. You've got the so-called S states and the so-called P states. And so you've got another 2 trillion electrons in this band, and it would be 6 trillion electrons in that band if there's 1 trillion atoms in our piece of sodium. And then you'd get to n equals 3. Each sodium atom has only 1 outermost electron in the 3rd energy level. Of course, each atom can hold 2 electrons in that energy level, but sodium, being element number 11, only has 11 electrons, so it only has 1 electron to put in that energy level there, which means that if you have a whole piece of sodium metal, this band is only half full. It has room in it for 2 trillion electrons, but only actually holds 1 trillion electron. That's why I shaded in the bottom half of it and left the top half looking empty. And then the still higher bands, you know, the 3p band and so forth, there aren't any electrons up there because sodium doesn't have that many electrons. Anyway, this business of having the highest filled band be only half, well, it doesn't have to be half, but the highest band with electrons in it being only partially filled, that's what makes metals good conductors of electricity. And actually good conductors of heat for that matter. The same free electrons that carry electric current also carry heat very efficiently. So get back to the chalkboard over here. Okay. So here's that uppermost band from the picture in the handout. And the bottom half of the band is filled with electrons. The top half is empty. You take this piece of metal and you hook it up to a battery. Risky proposition with sodium. Sodium actually explodes if it comes in contact with oxygen. You're better off using aluminum or copper or something like that, but that's beside the point. Any metal, the highest band with electrons in it is partially filled like this. Now, if you hook that piece of metal up to a battery, which makes the electrons in it start to flow, those flowing electrons have more energy than if they weren't. I mean, where does the energy come from to spin a motor or to make a light bulb glow? An electric current contains energy. So if the electrons in this metal are going to become part of a current, they have to move to a higher energy state. So an electron that might have been right there before you connected it to the battery, well, it's going to move up here to somewhat, I'm maybe exaggerating a little bit here, but somewhat higher in the conduction band. This would be just one electron, but lots of others around it are doing the same thing. So yeah, that's okay, that works. Try and do the same thing in an insulator. Here's the band structure in an insulator. The highest band containing electrons, the so-called valence band, is full. The next band up, which would be the conduction band, see in a metal, the valence band and the conduction band are the same thing, but in an insulator, they're not. So the electrons in the valence band are here, and you hook it up to a battery, which means to flow as an electric current, the electrons have to gain some energy and move up, higher up the chart means more energy. Trouble is, that's not allowed, okay? You're between bands. The energies in between are forbidden, just like the energies between energy levels in an atom are not allowed. An electron in a hydrogen atom has to jump from one energy level to another. It really can't exist with any of the in-between energies. And yeah, these are the in-between energies where electrons can't exist. So because there is no available state of the proper energy, an electron can't gain energy and can't flow as an electric current. This type of thing also explains thermal and optical properties. If you have some sort of a crystal that's clear, a piece of metal is opaque because photons start falling on the thing, and electrons can absorb the photons by jumping up to a higher energy. But if you have some sort of a, like a diamond or a ruby or something like that you can see through, an electron that tries to absorb a photon is going to have to jump up to this energy. The amount of energy it gains has to equal the energy of the photon, but that would just land it in somewhere in this forbidden range here. The electrons are incapable of absorbing photons of that particular energy, which means those photons have to sail on through, and the thing is transparent. But that kind of goes off on a tangent a little bit. I was going to stick to electrical properties. So that's the band structure, and that's how it explains, that's how it relates to electrical properties, and actually that's what's written on the top of the next page. So as I already said, focus. In a good conductor like a metal, you've got a partially filled conduction band. In an insulator, you've got a filled valence band. Above that is an empty conduction band. And so there aren't any free electrons available to conduct electricity. Well, then there's this in-between class of materials called semiconductors, which, as you may have heard, are kind of important for our modern technology that our current lifestyles kind of revolve around. The most famous example of a silicon, or the most famous example of a semiconductor is silicon. There are others. Germanium is a semiconductor. A number of other compounds, gallium arsenide, and so on. At absolute zero, a semiconductor has the band structure of an insulator, in that you have a bunch of electrons in the valence band and the conduction band is empty. The difference between a semiconductor and an insulator is that the gap in between the two bands is very narrow. Don't quote me on the numbers, but I want to say that the gap in silicon is only something like 1.3 or maybe 1.4 electron volts wide. And in germanium, it's even narrower. It's only about 2/3 of an electron volt from the top of the valence band. I've been talking too long. I think my throat's drying out. From the top of the conduction band to the bottom of the valence band, which means if you aren't at absolute zero, if you're at room temperature, there's enough thermal energy making the electrons hop around that some of them are energetic enough to jump across the gap and land themselves in the conduction band. So at room temperature then, there are some electrons available to flow if you establish an electric field, and semiconductors will conduct, but poorly, because there aren't nearly as many free electrons as there would be in a metal, but they do, you know, the resistivity is pretty high, but there are, you know, if you hook it up to a battery, there will be a little current flow. Actually, there's more to the story than just these free electrons that have jumped up into the conduction band. There's also the so-called holes that were left behind down in the valence band. So that story goes like this. In the case of silicon, there are 4 valence electrons, okay? The outermost electrons are the ones that do everything. They form chemical bonds. They're, you know, the ones in the inner shells just kind of go along for the ride and never do anything. Silicon has 4 electrons in its outermost shell. And because of that, when it forms a crystal, actually it forms the same crystal pattern that you get with carbon in a diamond, where there are 4 bonds to its neighbors, okay? It forms 4 chemical bonds. You know, it's sharing electrons. It is what the bonding is. It shares electrons with 4 of its neighbors, and that's what holds it together as a rigid solid structure. Well, what if one of those electrons escapes? The temperature's high enough that everything's vibrating around enough that one of the electrons gets knocked into by something else, and that gives it enough energy to escape the atom, and it's a free electron now. It's up in the conduction band. Meanwhile, on the silicon atom that it just escaped from, now you've got a silicon ion. It's only got 3 valence electrons, but there are 4 other silicon atoms around it that are expecting to form bonds with it. So what it does is kind of like a little kid who sees the little kid next to him has a toy he wants, just kind of like, I'm bigger than him, and he just reaches over and he grabs it. You know, the kid starts crying. So the silicon atom steals an electron from its neighbor, and now it's got 4 valence electrons and can fit into a crystal lattice where everybody forms 4, you know, it's a pure pressure thing. Everybody's forming 4 bonds with their neighbors, and I want to do that too. Well, meanwhile, there's the silicon atom over there that's crying because somebody stole its electron. So it looks at its neighbor and decides to do the same thing and steals an electron from its neighbor, and now it can form 4 bonds the way it's supposed to. And its neighbor then steals an electron from its neighbor, which steals an electron from its neighbor, and this creates a unit of positive charge, which is free to move around in the piece of silicon. So in an absolutely pure piece of silicon, do the focus thing, okay. You have equal numbers. You've got free electrons in the conduction band, and if you hook the piece of silicon up to a battery, they'll start flowing in one direction because they're negative. And then there's the vacancies left behind in the valence band, which for all practical purposes behave like positive particles that will flow the other way if you hook the thing up to a battery. Okay, notice with these holes that we're not talking about free electrons. Any individual electron just jumps from one atom to its neighbor, a distance of roughly 10 to the minus 10th of a meter, and then that's it. It just stays there. It's the vacancy that's moving around, going anywhere it wants to in the piece of silicon. So in a pure piece of silicon, it's like a 50-50 proposition. You've got free electrons up here, you've got free holes down there. Where things start to get interesting and useful is what if it isn't pure silicon? Mixing in impurities is called doping. What if into this crystal lattice where everybody forms 4 bonds with its neighbors, what if you mix in some atoms that have 5 valence electrons, 5 electrons in the outermost shell? Well, there's only 4 neighbors around it that are willing to form bonds with it. The 5th electron is kind of useless. And I guess because its feelings are hurt or something like that, it just leaves home. It wanders off. And so when this happens, that's called a donor atom. An atom with too many electrons to fit into the lattice just kind of lets one wander off as a free electron. So it adds to the number of free electrons up there in the conduction band. Doesn't create any holes because it just, the atom that gave off the electron just sits there as a positive ion, forming 4 bonds with its neighbors. It doesn't do anything to try to replace the one that left. This would be called, if you dope up your silicon this way, that would be called N silicon. N as in negative. If you hook it up to a battery, the current is dominated by negative charges, electrons, okay? Because you now have considerably more free electrons than you would have in just pure silicon, you have made the silicon into a better conductor of electricity. I mean, it might still not quite be up to what you get with copper or silver or something like that, but it's, if you mix in enough of these donor atoms, it'll be a significantly better conductor than just pure silicon is. Well, it works the other way around also. What if you mix in some impurities that are trivalent? The outermost shell has only 3 electrons in it. Well, the atoms around it are expecting it to form 4 bonds, and it's only got 3 electrons. So what does it do? Well, just like the little kid I was talking about, it steals one from the atom next to it and becomes a negative ion. Now it's got 4 electrons like the neighbors expect, and it can form 4 bonds and fit into the crystal lattice. But now the neighbor has a problem, so it steals an electron from an atom that steals an electron from its neighbor, and so on and so on. So these trivalent atoms create holes. Once again, making the silicon into a significantly better conductor than it would be if it was just pure silicon. You haven't really done anything to increase the number. I mean, yeah, there's a few thermally excited electrons up here in the conduction band, but there's a whole lot of holes down here in the valence band created by your donor atoms with more free charges available. When you hook it up to the battery, you get a bigger current. You've made it into a better conductor. So when the electric current is a bunch of positive charges, or primarily, like I said, there's a few electrons up there in the conduction band, but conduction is dominated by positive holes. You've made P silicon. So what do you suppose would happen? Boost this up again. What do you suppose would happen if you made a piece of silicon or germanium or some other semiconductor material that was P-type on the one end and N-type on the other end? One way of doing this, it doesn't work that well for the little miniaturized components that are the backbone of modern electronics, but as a simple way to understand, if you had a little crucible full of silicon and you slid it into an oven, so you melted it in there, then while your silicon is all melted, you sprinkle in some donor atoms and you make it N-type. Well, then you slide it halfway out of the oven so that the one end solidifies, but the other end's still liquid, and you give it a good dose of acceptor atoms. And so that becomes the dominant thing on that end. And then you pull it the rest of the way out and let it cool off and harden up. So you've now created a semiconductor that has in the middle of it a junction between P silicon and N silicon. And the useful thing about this is it only conducts electricity in one direction. Okay, it's a one-way street for electricity, which is what you need, for example, in a power supply where you want to convert AC into DC. Almost any electronic device, computers, televisions, your cell phone, they all run on direct current. But the outlet that you plug it into is AC. So virtually any electronic device has to contain a power supply that converts AC into DC. And it probably is going to change the voltage also. There'd be a transformer in there, but that was a topic for another day. The topic today is how do you get the electricity to flow in only one direction, which is what direct current means. Well, if you go back to, the radio technology of 100 years ago, this was done with vacuum tubes. You'd have a, probably get tired of looking at that. This is too much better, but you'd have a vacuum, glass tube with all the air pumped out of it. And on the one side would be a hot filament similar to a light bulb filament. It's hot enough that electrons are cooking off of it into the surrounding space. The high temperature gives the electrons enough thermal energy to escape from the surface of the metal. You apply a high voltage to accelerate the electrons and shoot them across the tube where they're collected by another electrode, and they go on down through the circuit from there. The thing is, if it's an alternating current, the electron, it flows in one direction, okay, fine. When it turns around, tries to flow the other way, the other electrode isn't hot. It's not giving off any electrons. So when it goes back up, it can't. You just get pulses of electricity going, here's your graph of current as a function of time. We call it an alternating current because the direction alternates. First it goes one way, then it goes the other. Well, if you send this through a diode, it flows in the one direction, and that's no problem. When it tries to turn around, it can't, so that gets cut off. And then it tries to flow that way, and that works. And then when it tries to turn around, it can't. And so your AC gets converted into pulses of DC, which can be smoothed out into a continuous smooth flow. You store up the charge in a capacitor and you can smooth that out. But that was a topic for another day also. Right now, we're interested in the fact that a diode rectifies. You don't need to know that word, but it turns AC into DC. So the original diodes were vacuum tubes with 2 electrodes, diode, 2 electrodes. But the problem with vacuum tubes is they're bulky, they're somewhat unreliable, and worst of all, they're power hogs. Keeping that filament hot uses a lot of energy. So solid state components have replaced most vacuum tubes today. So we've got this PN junction. And you hook it up to a battery the one way, and that makes current flow through it in one direction. And you hook it up to a battery the other way, and that makes current flow through it in the other direction. So when the current is, conventional positive current means the direction that positive charges would flow. Whichever way the current is flowing, that's the direction that the holes move because they're positive. In case you didn't figure it out, H for hole, E for electron. Here the current's flowing the other way, so the holes are going that way instead. Electrons being negative, they go the other way. Well, if you hook your solid state diode up to the battery this way, then this is actually the negative terminal of the battery here. Electrons flow down this wire from the negative terminal of the battery into your piece of silicon. This wire is dumping electrons into your diode by the bucketful. Over here, the battery is sucking electrons out, creating holes, which go the other way. So when the holes and the electrons meet at the junction, they combine with each other. And that all works very nicely, and you have a large current flowing through the diode. You turn it around so everything flows the other way. Now you're sucking all the free charges out of the junction. Electrons flow away from it, holes go the other way, so they flow away from it. Remember what a conductor is in the first place. A good conductor of electricity is something that contains charges that are free to flow. So when you hook it up to a battery, you get a flow of charge. If you go sucking all the charges out of your junction, you've just made it into an insulator, okay? There is nothing in here that's available to flow in the electric field from the battery. And well, there's a lot more to that. I mean, if you take a course in solid state physics, there's a whole chapter on this kind of thing. But to make a long story short and leave out some important details, you make the thing into an insulator, current won't go through it. So this does what the vacuum tube diode would do without having to keep a filament hot or any of those undesirable characteristics. It conducts electricity in only one direction so that it will make AC into DC for you. And I'll bet on the next page I have transistors. Yep, next page is the last page in this unit. After that, I'll give my voice a little rest, have a little something to eat, and I want to record section 14 today also. So when you see me in the same shirt, don't go, ew, he's wearing the same shirt again. It's the same day, okay? So instead of a junction between P silicon and N silicon, what if you have two junctions? P and P, or a minor variation is if you make it NPN. I didn't feel like drawing two pictures when there wasn't that much difference between them anyhow, but the transistors come in both varieties. To be precise, this is what's called a junction transistor, which are actually the most common type of transistor as I understand it. The most common type today is what's called a field effect transistor. That's what they put on all the little microchips for like computer memories and that sort of thing. Yeah, that's just a variation on the same general sort of idea. You've got a current flowing across the thing like that. Almost, the thin layer, the N layer in the middle is quite thin. So the holes that are flowing along through the P silicon over here, when they get to that thin N layer in the middle, a lot of them just flow right through it and keep on going. But some of them get caught on the donor atoms in the middle, and a layer of positive charge will build up. So if the center layer of the transistor gets all charged up real good positive, what are these holes over here going to think about that? Well, they aren't going to want to go over there. Plus repels plus. You've built yourself a wall of electric charge in the middle of the transistor that repels the charge trying to flow toward it, and that turns the current off. Unless you drain those charges out of there as quickly as they accumulate. If you get a current flowing down this third wire, the wire that's connected to the base, in a junction transistor, they call it the base. In a field effect transistor, they call the middle layer the gate. Gate's a good name because that's what it does. It lets stuff through or it doesn't, depending on whether the gate is open or shut. If you drain the charge out of there, then the current flows on through. A transistor is a valve for electricity, okay? You open the valve up by draining that charge out of there, and that lets the current flow through. You close the valve by not letting any current flow down this wire, and then the center layer just charges right up in no time, and that turns the current off. The valve is closed. Let's see. This does a couple of good tricks. It serves as an amplifier. In the old days, vacuum tubes with more than 2 electrodes were used to amplify signals, triodes and things like that. As I understand it, if you had a time machine and decided that you wanted to hear Lincoln give the Gettysburg Address, you should probably get there early so that you get a front row seat, because it would be hard to hear in the back because, well, I don't know how big the crowd was. Maybe that's a bad example, but in some situation where there's a big crowd, if you got like, 100 other people between you and the stage, you weren't going to hear anything in the 19th century. What we do today is we give the person on the stage a microphone, and there's these 2 great big speakers on either side of the stage, and boy, you can hear that without any problem. You take the signal and you amplify it. So what you do is you've got, well, to amplify something that much, you would use more than 1 transistor, but you've got this, what you do is you attach the microphone to this wire here, the base, okay? And as the speaker talks into the microphone creates a current, a small current, a fairly weak current, that varies with the pattern of that person's voice. As this current here varies with the pattern of the person's voice, how much charge collects in the middle of the transistor will vary with the pattern of the person's voice, which means how much of the larger current that's flowing across the transistor this way. The valve opens and closes partially with the pattern of the person's voice, which means how much of this current gets through there varies with the pattern of the person's voice. And you have now taken a much larger current and sculpted it to the same waveform, which can now drive a loudspeaker to create a louder version of the person's voice. So one thing transistors do is amplify. The other thing is, as I mentioned, an integrated circuit is basically just billions of transistors. Well, I mean, it may have other components on it also, but something like a computer memory. The information has been encoded as a whole bunch of ones and zeros. Each one or zero, each bit of your digital information is stored in one transistor. A transistor is basically a switch, a valve. If the switch is turned on, I believe on is 1, off is 0, unless it's the other way around. It doesn't matter really. Each transistor, by either being on or off, can store a 1 or a 0, and we've learned to make really large numbers of transistors that are really absurdly small so that you can fit like billions of them, many billions of them, on an integrated circuit the size of a postage stamp, and that's what you have in well, not only computers. I mean, for crying out loud, there's computers in everything now. You know, washing machines and everything, cars full of computers. So anyway, that's the story of that. So I've got some questions here. I didn't really, well, number 6, I didn't really get into anything with a lot of numbers in it, talking about solid state electronics here. I've got some conceptual questions for you to answer. And then number 7 at the bottom, that's got some numbers in it, but let's boost that up where you can see it if you're trying to do all this off the screen. Let's see, that's a good spot there. So, yeah, you know, if I get it a little further back, you can get the rest of the, actually, I think I need to boost that slightly higher. Hold on. I'm trying to get all of number 6 in there at the same time. There we go. That is optimized, except for the focus. Okay. Pause it, do that, parts A, B, and C, bunch of conceptual questions. And now I'm assuming, well, you know what? I got to erase this over here. Number 6. Part A, energy bands of a certain solid are as shown. Is this material? Well, a good conductor is one where the highest band containing electrons is partially filled. And that's exactly what's shown in the picture. I guess you can't really see it, but the picture there in part A of number 6. You got that half full conduction band, and that makes it a good conductor. And maybe I don't need to write that down, but I will anyhow. Which probably doesn't do any good because nobody knows how to read cursive anymore, but part A is a conductor. Part B, does having electrons flow into the middle layer increase, decrease, or have no effect on the main current flowing horizontally? Well, let's see, this is an NPN transistor. So it's electrons flowing through it. If electrons flow into the center layer, that's going to charge that center layer up, which will repel the electrons over on the left that are flowing toward it. So that will decrease the current. The more strongly charged that center layer gets, the more electrons collect in it, the more repulsion the horizontal current is going to feel as the electrons try to get through there. So B would be decrease. And then part C, draw a few holes in each picture. Okay. So we've got one where the current is going that way. Actually, I guess I've got the current going the same way in both of them. It's just which end is which gets switched. This one, N is on the left, P is on the right. This one is the other way around. Well, I don't think I need to draw a lot of particles. I mean, one sort of makes the point. So there's a typical electron in here. Because it's an N semiconductor, the flow of current is dominated by electrons. Over here in a P semiconductor, the flow of current is dominated by holes. Conventional current is goes in the direction of positive charge flow. So the holes are going that way, and the electrons go the other way. And over here, once again, positive charges go in the direction of conventional current, and negative goes the other way. And then the question says, in which case is the current large? That would be here, where the wires create a lot of charges at the ends, which flow toward each other and combine at the junction. That's where you get a large current. You get a small current is where the electric field from the battery sucks all the free charges away from the junction, leaving nothing in that region to make a current out of. There are no free charges that can flow, so you don't get a flow charge. And then I should probably give you a glimpse of problem number 7. And then that'll be it for Unit 13. LED, a light emitting diode. When I was talking about using diodes to make AC into DC before, diodes that are used for that purpose, any energy that's lost by the current flowing through it is made into heat. But if you make a diode out of the right materials, then they will give off energy in the form of light instead. And that's a light emitting diode, which is becoming a pretty important technology, actually. So what is the color of the light it gives off? Well, what happens is that you've got an electron at the bottom of the conduction band, and you've got a hole at the top of the valence band. When the electron drops into the hole, it loses energy equal to the width of the gap between the two bands, which in this case is the 1.88 electron volts. So, or, you know, if the electron is a little further up in the conduction band, it might give off a somewhat higher amount of energy, but this is where the threshold is anyhow, is at 1.88 EVs. And the light from a diode is not completely monochromatic, but anyhow, you just stick that into E equals HF. And well, you have to find the wavelength and so forth. But anyhow, pause it if you haven't already, figure it out. And then let's put it over here. That's a good spot. Just got to clean it up. Paper, don't want to let go of each other. There we are. Okay, so the energy of the photon equals the energy lost by the electron as it falls into the hole. And it's going from one side of the gap between the bands to the other side of the gap. And that means the electron loses 1.88 electron volts. Convert that into joules. Then, and again, you might want to do the math first and then the manipulations, or I combined the formulas first and then filled the numbers in instead of actually coming up with a number for the frequency, because I don't care about the frequency. E equals HF, where F equals C over lambda. If you put them together, E equals HC divided by lambda. Planck's constant. Speed of light. And yes, not Kelvin. I was hasty. If E equals HC over lambda, it follows that lambda equals HC over E. Skipped a step. Sorry about that. For those of you who are sitting out there going, what is he doing? The question asks for the wavelength. So the wavelength equals HC over, this is E. .60 times 10 to the negative 7th of a meter, or 660 nanometers, if you'd rather avoid scientific notation. Okay, so there's section 13 all in one sitting, or, you know, it's a video. You can watch 5 minutes at a time if you want to, but I'm going to stop it here. And in a little while, we'll do the last part of the course.